Of course, the first place we saw acids in our organic modules was when we oxidized primary alcohols. You take a primary alcohol, you do mild oxidation, you make an aldehyde, or you do strong oxidation of the primary alcohol or the aldehyde, and you make carboxylic acid. Because we don't care about stopping at the aldehyde, we can use any old oxidizing agent, potassium permanganate, the acidic chromium 6 and so on that we've discussed before. So we've now actually seen this 3 times in the alcohol module, in the aldehyde module, and now in the acid module. That's another cute way that you can make benzoic acid, starting with alkyl benzenes. Okay, you've got to have a carbon with a hydrogen on it bonded to the benzene ring, and then these other R groups here. Oxidation level of this one would be, a number would be -1 because you got the carbon bonded to a hydrogen. Nothing fancy about this carbon, so oxidation level of 0. If you oxidize it using any of our reagents, well then you turn whatever this alkyl group is, as long as it's got the hydrogen, whatever you turn this is, you turn it into just the acid group. So the hydrogen is needed there, throw in a couple of oxygens, and then the R and the R prime just vanish off into wherever not wanted alkyl groups go. So a good way to make benzoic acid if you want to start off with an alkyl benzene, and of course you can make alkyl benzenes by taking benzene and doing a Friedel-Crafts alkylation or a Friedel-Crafts acylation on that, all of which we have discussed before. Now, there's a couple of reactions that are there on the A-level spec, one of which is somewhat incorrect on the A-level spec, one of which we've talked about before. So I'm just going to squeeze them into this slide here. Okay, first of all, the opposite of this is decarboxylation. Okay, so according to the A-level script, you take an acid and you heat it up and you make the alkane from it and you lose CO2. Okay, now it's a very misleading thing to think that this is that easy. Okay, just about all the time, it's not the acid that's doing the reaction, it is the conjugate base of the acid. So you have to do this reaction with sodium hydroxide or calcium hydroxide. So for example, take the acid, react it up with 2 sodium hydroxides. Well then, instead of seeing actually CO2, you make the sodium carbonate, you make the alkane. Same type reaction with calcium hydroxide, but instead of sodium carbonate, you make calcium carbonate. But again, you see the CO2 from the acid group has gone away to the sodium or the calcium in part of the carbonate, and you've made the alkane. But like I said, this goes via the conjugate base. So the first part is the hydroxide, strip off the H, much easier then to decarboxylate it, get rid of the CO2. Where it does work well is with the dicarboxylic acids, in which you just now heat this up and it quite readily kicks out CO2 from one of the acid groups, okay, leaving behind the mono acid. So this is, it seems like a funny way in this case to get ethanoic acid, but it can have some significant synthetic capabilities. So decarboxylation, not quite as simple as just heating up any old acid. Most acids you have to do it in basic conditions so that you're going via the conjugate base, but it is a very useful reaction for dicarboxylic acids. And then the other one, just to squeeze in on this slide, is that one of the reactions of acids is, of course, reduction. Okay, we've talked about that before. You can often use sodium borohydride in aqueous conditions to do reductions. You can't do that with carboxylic acids. If you want to reduce a carboxylic acid, as we've talked about in the previous module, you have to use lithium aluminium hydride, and you have to do it in anhydrous conditions. There are, of course, other ways to make carboxylic acids, and 3 of them I'm going to mention here that have been noted to an extent in other places in this course. Two of them involve starting with what I call an alkyl halide and you call a halogenoalkane. As you might remember, halogenoalkanes absolutely love to undergo nucleophilic substitution, in which a nucleophile comes in, grabs the R, kicks out the X. Well, cyanide, Cn-, is an absolutely awesome nucleophile. And so one of the other nucleophilic substitutions that we listed back in the halogenoalkane module was exactly this, cyanide replacing the X to give you a so-called nitrile. I would call it an organic cyanide, but nitrile is the better thing to do. I'll have a little movie on nitriles in the next module, but for now, all we need to know is that when you take nitriles and you hydrolyze them with heat in acidic conditions, you make the carboxylic acid. Now, something that I thought was rather cute as I was noticing it this time, I'd never really noticed it before or thought about it before, was that this looks like it's an oxidation, doesn't it? Because you're adding in oxygen atoms. Of course, you're also adding in a hydrogen, which would make it a reduction. Well, as it turns out, when you think of things in terms of oxidation numbers or even the reviled oxidation levels, it's not an oxidation at all. In the nitrile, the carbon bonds to the R, well, that doesn't affect the oxidation number or the level. Triple bonds to a nitrogen, which means it has an oxidation number of +3 and an oxidation level of +3. The carboxylic acid, the carbon bonds to the R, doesn't do anything. Double bonds to an oxygen and single bonds to the oxygen that goes to the H. So that's, again, oxidation number of +3, oxidation level of +3. So even though you're throwing in extra oxygens, it's not an oxidation. It doesn't change the oxidation number, or if you believe in these things, the oxidation level. Anyway, that's one way in which you can go from a halogenoalkane to a carboxylic acid via the nitrile. Another way to do it, and this is something that alkyl halides do that I mentioned in the extension material, not for the halogenoalkane module, but for the aldehyde and ketone module. And that is that if you take alkyl halides, react them up with magnesium in anhydrous conditions, usually ether, then you make this so-called Grignard reagent. Now, Grignard reagents are amazingly useful reagents in organic chemistry. One of the most versatile organic synthetic reactions is to make a Grignard reagent from an alkyl halide and then react it with an aldehyde or a ketone to make an alcohol. And of course, alcohols are extremely versatile reagents. And what you've done is you've made an alcohol in which you've thrown in an extra bunch of carbon atoms, which is very important. Anyway, one of the lesser reactions of Grignard reagents is to take a Grignard, react it up with carbon dioxide, and you make this funny looking species here. Now, it's written like this just to keep everything all balanced. What it effectively is, though, is if you recognize this little bit here, the RCO2, which is a minus, is the conjugate base of a carboxylic acid. So it's an anion with a magnesium, which is a 2+ cation, with a halide, which of course is a 1- anion. But the important part is this conjugate base of the carboxylic acid, which then, when we react this whole species now with H+, gives us our carboxylic acid. Now, important thing to note here in the synthesis is in both cases, starting with the alkyl halide, whether we go through the nitrile or whether we go through the Grignard reagent, we've ended up with a carboxylic acid that effectively has an increase of 1 carbon atom. And I've mentioned before how important a part of organic synthesis it is that you have a way to change the number of carbon atoms from one species to another. Well, this is a very nice way to increase your carbon atoms by 1. Another reaction that you've seen before, again, involves a nitrile or a cyanide, is taking a aldehyde or ketone. You might remember this from the aldehyde or ketone module. We take this, we use potassium cyanide or sodium cyanide, which has the Cn-, which again, very nice nucleophile. Here it's not doing nucleophilic substitution as it is up here. Here it's doing nucleophilic addition. So anyway, when we take that Cn-, we have the Cn- attacking this carbon, nucleophilic addition, putting an O- here, and then the H is there to put a proton on the H, and we get this so-called cyanohydrin. Okay, now that was a very important reaction back in the aldehydes and ketones because it was a big illustration of nucleophilic addition. But I also mentioned that if you take this cyanohydrin, you can do two things with it. You can reduce it and you make an amine, which is the subject of the next module, or you can oxidize it. And it's, of course, not oxidation here, but hydrolysis to get that same cyanide or nitrile group to carboxylic acid group. So again, I slipped up when I said oxidize it because again, you're not oxidizing it, you're hydrolyzing it. So anyway, a couple of other ways to synthesize acetic acids, both of which, or three of which, in some extent have been mentioned before.